Well, I want to thank all our speakers who are going to present today at the Disruptive Technology panel. It seems that every time we have this, we have a different definition of what disruptive is, so I can't wait to see how you guys define it today. I'll give you my definition. It was coming in from the airport yesterday and having a really nice Uber driver tell us where to get the best beer in town. And I thought, Uber has kind of changed the way you do business nowadays. And while it's not a high technology sector, it certainly is disruptive. And the technology behind it has enabled all of it. So I'm looking forward to seeing what folks think about in terms of disruptive technologies as we move forward here. Basically what's going to happen is each panel member is going to give 5 or 6 minutes talk, and I think Steve is going to be our sergeant at arms here when it comes to enforcing the 6. Look at this, he comes prepared. A view of their disruptive technologies that could change the HPC industry. And here we're not just talking about the HPC sector, but really the user base and the larger, because that's really a theme I think here that we're seeing today is how does HPC affect industry and economic and industrial competitiveness really at the global scale. And no sales or marketing slides allowed. I have no idea how we're going to enforce that. Then we'll ask each panel member to respond to a few key questions about the technologies that they presented. I want to introduce the members of the panel. We have some really smart folks here from Dell, D-Wave, IBM, Lenovo, Mellanox, Ryft, Seagate, and Cray, who must have been a late entrant because they're not in alphabetical order there. And the questions that we really want you to be thinking about, and the audience should be trying to listen to frame whatever questions they'll have is first off, what is most needed to bring to market faster or with more certainty the disruptive technology you're referring to? What parts of the market will use it first, and will it likely become a mainstream technology? And perhaps in many cases, mainstream isn't the ultimate goal. If you can establish some key sector, some key capability, mainstream is ultimately not, the end-all, be-all when it comes to an interesting disruptive technology. And finally, I think one of the most important questions that we'd really like people to consider is what partners, if any, would you like to, would help bring it to market sooner? So that's the question, and just for the sake of complete objectivity, why don't we just start off with representative from Dell.
So, I was thinking about this before, and I'll simply say that up until an hour ago, I wasn't planning on being the panel, so I wasn't entirely prepared. My colleague in crime, Matt, is up in his room someplace not feeling well. But thinking about this, and we kind of look at HPC in the classical market pyramid side, and by the way, I have no slides, and by definition, anything I show would be marketing slides. So from a market period, so we're always looking at how we're impacting the market from the standpoint of sort of up on the pyramid of how we're advancing the technologies and so on to build bigger and better and faster systems and so on, as per the ECP presentation earlier this morning. But we're also looking at from the standpoint, how do we broaden the market? So, I like to think of it, how do we make HPC both more powerful as well as more pervasive? And so thinking in those terms, I sort of was thinking, what trends might we think about and what might impact from both of those perspectives. And the first one that came to mind, and the presentation just before from what would have been my colleague if I had stayed at HP, around machine learning and so on, is certainly one of the areas that came to mind immediately. And we're seeing machine learning as a technology and everything that comes with it is, and with the movement into analytics and more data-centric HPC and high-performance data analytics, nod to Steve, is really creating a dynamic that's broadening what we think of as HPC. And we're seeing it simply from the broad nature of the customers that we as Dell EMC talk to, are asking us about HPC who never would have spelled it before, because they're starting to see applications of analytics and machine learning in everything from marketing, fraud detection, certainly in medical applications, and so on. It's just popping up in all sorts of interesting places. It's great, Arno is here in his former life at PayPal and some of the things that they did around fraud detection. at the end of the day, it's machine learning. And that is creating a whole set of new application areas that's expanding the market, and that expansion is, I think, very disruptive to everything that we do. Simple fact that we're talking about it so much, it's clearly disrupting us. The other thing in terms of the performance angle on that I thought about was, it goes alongside with that a little bit, is what we're seeing as the change in the memory hierarchy of the systems that we're developing. So I'm old enough to know, to have worked on systems that basically had a processor, had memory, and a floppy disk, with nothing else, no cache, no nothing in between. So yes, I did know about Robbie the robot, by the way. And now, of course, there's multiple levels of cache. There's multiple levels of main memory. We're starting to see things like 3D XPoint coming out, NVMe coming out, and so on. On the storage side, it's not only rotating media, it's also SSDs and so on and so forth. So we're seeing the multiple levels of memory hierarchy that is changing the way we deal with volumes of data that has to happen in order to be able to handle the more data-centric sets of HPC workloads that we're doing. That is also changing the way that we build bigger and better and faster systems, not only to just do compute, but to handle the enormous volumes of data. So, we look at it obviously in our new entity having EMC and Dell coming together, that starts really creating some opportunities to create a whole new wave of HPC systems that would be able to provide the capability to manage volumes of data that we couldn't conceive of before. And again, disrupting the industry in the process. So I think I'm early for a change. That's because I had no slides.
My name is Gary Valley. I'm from Ryft. We've done a few of the HPC User Forums in the past, and traditionally, everything we've talked about has been about a data analytics accelerator, an actual appliance, a physical appliance. If you want to flip to the next, well, there we go. Perfect. And so those devices still exist in sort of the Ryft context, in that if you want to go fast, you want to plow through a lot of data. We're still building those devices and playing that game. But recently, we've had a shift in focus at Ryft, and that's come along with some of these sort of cloud or virtual vendors, where we're starting to pull some of these HPC concepts into a virtual context. So in our instance, that's going to be Amazon's cloud is now going to start introducing FPGA technology into their cloud. So any user who has access to that is going to be able to fire up instances with either GPUs or FPGAs or any number of different hardware platforms underneath that. And so Ryft is starting to shift focus a little bit, in that rather than focusing on building sort of the hardware attached to these HPC or HPDA type applications, we're starting to focus more on a middle layer where we can give people access to the correct hardware for the types of workloads that they're actually implementing. And we're allowing them to do that on whatever platform they're running. So if somebody's on premise, we're going to allow them to bring devices into their infrastructure and actually run on-premise solutions. Or if they're in a cloud situation, you could potentially still get access to those different types of hardware for those specific workloads in that environment. And so obviously, since we're sort of sliding away from a little bit that sort of building an actual data accelerator, et cetera, underneath the covers, our focus is more on sort of these end user applications. How do I sort of give this sort of HPC concept or HPDA concept all the way up to that end level user? So it's almost a seamless stack. Me, the solution developer, can build my application on a simple API, and if there's a different hardware stack underneath the covers that makes sense, I can trade that hardware stack and keep the API the same. It lets me enable some applications that I couldn't before. And so right now, Ryft is in some, and we can't talk about them because of NDA things, but Ryft is in some evaluations right now with a bunch of different folks talking about a variety of different applications based on all these different types of hardware stacks. Everything from sort of genomics environment to the financial space to cybersecurity. And the reality is underneath the covers, there's a simple API that's allowing us to enable almost any application we can dream of with the correct hardware stack underneath. And so I'm going to be very short here. So the sort of game here is that middle layer in between those two blue bars there is we're going to provide a list of libraries. And the idea is eventually the end users, there's hardware developer resources out in the world today, but generally those are expensive and they're very specialized. We want to allow those people to write to a specific API that gives users at the very top of that stack access to the fastest sort of implementation of that algorithm that they possibly can receive. And so that's where Ryft is trying to play, is we're going to help build that sort of middleware layer where we build on top of a platform, users can interchange hardware underneath for the workload where it makes sense, and their application remains the same at the top.
Hello, my name is Jerry Lotto, and I'm relatively new with Mellanox, been there less than a year. I wanted to start out with this slide, but as I look around the room, I realize I don't need to tell this group anything about the history of HPC. The point of this slide is simply to call out 3 transformative events that have occurred. The first, of course, is the symmetric multiprocessor machines gave way to Beowulf architecture clusters. The second, the transition from single-core to multi-core processors, allowing for a greater degree of parallelism than ever before. And then the most recent, which we've talked about, several people have talked about today, is the issue of co-design. The idea that heterogeneous architectures can realize acceleration by dividing up an application and focusing the components or the algorithms on the hardware that's optimized for each component of that algorithm. Now, Mellanox is a networking company, an internet company, and there are 2 different philosophies for networks. In a CPU-centric architecture, the network is a fast pipe, but data needs to be delivered all the way to an endpoint before any processing can occur. What Mellanox is trying to do is to promulgate this idea of a data-centric network. It honors the principles of co-design, actually introducing a new category of coprocessor in the network. It creates the opportunity to analyze data as it moves. We can use something like an MPI all-reduce collective as an example of this. In the CPU-centric situation on the left, you see in the upper left-hand corner where the root process is running, every node participating in this collective needs to deliver its results. There's a bottleneck that's created there. And even if the network latencies and bandwidth are very good performance, the communications fabric latencies tend to go up around 30 to 40 microseconds in situations like that. On the right side, you see a data-centric approach where the network switches actually participate. They recognize the collective, and they can perform inter-collective operations. By doing that and just delivering the result, you can see how the net amount of data that needs to traverse the fabric is reduced. It has a secondary benefit of removing that bottleneck because the end packet is a single result that needs to be delivered to the root process. And all of the processing that that root node would have needed to perform in order to could do the computation involved in the collective has been done already. Now, Mellanox makes end-to-end networking products. You're probably familiar with HCAs and switches. We also have accelerated HCAs with Innova, FPGA equipped, and Bluefield, ARM array equipped adapters. But the technologies that each of these products support and introduce, things like RDMA, Core Direct, et cetera, are the key to the message that I'm trying to deliver. And you see with the quantum and switch IB2, we support SHARP. Stands for Shared Hierarchical Aggregation and Reduction Protocol. And SHARP is the method by which we can provide these offloads and do the computation on the fabric.
So my name is Denny Dahl. I work for D-Wave. We make a quantum computer. This is going to sound like a planet report or a status report from some distant planet. You know, it doesn't really fit into the mainstream here so much. So I've been living up there in Los Alamos for the last 16 months, and about 12 months ago we installed D-Wave 2X. It's our third generation system. It's a quantum computer. And what I just want to talk about is not the hardware, not quantum mechanics, but I want to talk a little bit about the experience at the lab. I've been at the lab trying to help users wrap their head around our programming model. Our programming model is very different from classical computer. So, you know, I think right away that kind of qualifies us as disruptive technology. The thing that's really dramatic is the activity at Los Alamos that's been focused on the quantum computer. And by the way, I should apologize to Candy Culhane if she's here, because I stole the last slide from her, and maybe this one too. So at the lab, everything, the research is all tied to projects. The projects are tied to charge codes, and so money is sort of doled out to allow people to you know, undertake exploratory projects and other kinds of projects to let them, you know, get their feet wet and learn about this technology. As you can see, there's been a lot of projects kicked off over the last, you know, I guess year, 24 of them. And they wouldn't really qualify as applications. They're not, you know, kind of at the level of, say, pharmaceutical or oil and gas or financial. But the researchers at Los Alamos are sort of systematically learning to think about this new programming model and you know, sort of peeling away the layers of the onion and trying to figure out how to build tools and kind of raise their level of understanding so that they can actually start to think about, you know, applications. But the thing that's really driving all this is the promise of performance, and so that's what I'd like to talk about for the next couple of slides. The particular project I'm going to talk about is this one here, number 9, inferring sparse representations for object classification. So it kind of fits into this world of machine learning. And this was work done by this team of 5 people at the lab. This talk actually was presented over at the Center for Nonlinear Studies a few weeks ago. And it was really great. I'm just going to cherry pick a couple of slides out of there that do some performance comparisons. So these comparisons are all between the D-Wave system and then a classical solver, commercially available one called Gurobi. And the way to understand these slides is that we're looking for an energy here. Lower numbers are better. And then the real question is, how long did it take you to get there, and what's the quality of the answer? So in this case here, you see that the D-Wave system and Gurobi are getting same quality answer. D-Wave typically runs in a few seconds. In this case, Gurobi is 480 seconds. In this case here, quality of the answer is identical. D-Wave is a few seconds, Gurobi is 2,300 seconds. It's a larger problem. Then going on, in this example here, the D-Wave actually got a slightly better quality answer than Gurobi. Again, our execution time is a few seconds. Gurobi is somewhere over 9 hours. And then in this last comparison, the quality of the answer that came out of the D-Wave system is quite a bit better than the Gurobi answer. And Gurobi got cut off at 9 hours here. And D-Wave execution time is a few seconds. So this is the promise. You know, this technique, this kind of quantum computer, is not amenable to all problems. There's a tremendous amount of art just associated with identifying a kind of problem that is amenable to this platform. The community as a whole, as small as it is you know, still in the early part of this learning curve. So whether an application that you care about can be mapped onto this kind of architecture, that's a hard problem in itself. There's more hard work to be done to actually figure out how to write the code. Algorithms are typically very new, very different, you know, not familiar to us. So I would say, I'd close by saying, yeah, we qualify as disruptive. These are what our systems look like. This is our factory floor right outside of Vancouver. The final assembly happens up in Vancouver. The chips are actually fabricated here in the US. And the thing that's the big challenge for us is you know, building a community, an ecosystem of users who can start to think about these systems, map problems to them, build tools, you know, put open source projects up on GitHub. That's the real challenge facing us now. And to the extent that we're disruptive, you know, it's driven by this performance advantage, and then also by the notion that, you know, potentially we'll be drawing people from the community of, you know, HPC programmers. So I'll stop there.
Well, good morning. I'm Chris Lindahl from Cray. I want to start by, there was a great question this morning about whether or not we were seeing a fork in the architectures from one type of computing, or traditional HPC simulation, and big data computing. And at Cray, we don't think that we're seeing a divergence there, but we are seeing it at the microarchitecture level, perhaps. So as we see these microarchitectures diverge, trying to eke out the most performance and efficiency out of those, we're going to need an adaptive system and a flexible network and a common and extensible software stack, really, to bring those together. And with those things, we can drive convergence to one resource. And it's that convergence that's disruptive and changes the way that people will do business. So we've been saying this for a couple of years and presenting this as our vision. Today, I want to use a couple of customer cases and use examples to give a view of where we are in that, realizing that vision. So I want to start with Professor Wendy Tam Cho at University of Illinois and NCSA. And what she's done is she leads a group of people who are attacking gerrymandering and and drawing the districts for elections politically. And years ago, she came up with this concept of using computers to analyze demographic data, deeply analyze demographic data, to draw fair maps and use those fair maps to compare them to what's being proposed and be able to judge that proposed map based on what would be considered fair maps. Well, previously, you could only get to about 10,000 maps, and it wasn't statistically significant enough to make a compelling argument. Well, with Blue Water, she's now able to do billions of maps. And they're able to take that and analyze a proposed map to determine if it's a fair map or if it's been drawn politically. They're using this as part of planning to drive behavior, as part of litigation, and even to avoid accidents. Another example is a little bit more from our traditional simulation type thing, workloads, where NOAA and NCAR have developed the new national water model. So in this case, they used to have less than 4,000 sensor points, observation points, and they would generate their forecast data. Now they're able to use nearly 8,000 observation points and generate forecast points for more than 2.7 million points. And they're able to do that every hour to determine water rates and whether they're rising or falling. So this is a little bit more of a blending where you see both workloads operating on the same type of a system. I want to use one final example, and that's with Petroleum Geoservices. And they're an innovative company that does 3D seismic imaging. And one of the things that they've been looking at is how they can streamline their process. So in this is an example of a FWI code, and it's a multivariate optimization problem in which you would run the code, observe a residual, make some decisions, make some tweaks, run it again, and continue that to iterate on that loop. And if you look in the top right, that's the source data. That's what we're looking for in that problem. And conventionally, through that iterative process, with that overburdened resources, Dr. Go said, of an expert making a decision on the next thing to try to get better. After a few iterations, you can get something like that middle picture that makes it look like you're able to start seeing, yeah, we're getting a good sense of what's underneath the water there and where we can take things. Well, this still requires a lot of expert analysis and intervention. And PGS decided to go to Rice University and ask for some help in creating a machine learning variant that looked at how to address that next steerable variation quadrant. And taking that and running it back as part of their workflow, they're able to do what you see on the bottom. Again, many iterations, some of them not so great perhaps. But in the end, they're able to show better results faster with less intervention and requirements from their experts, freeing their experts to work on other things. All this on one system, and it's that interaction between the workloads where we're currently just now getting to that's going to be really exciting, where the output of one can dramatically influence the other immediately.
So we're all setting up. My name is Scott Crowder. I am the CTO for IBM Systems. So I run technical strategy, transformation. But what I'm here to talk about today is something else that I run, which is commercialization of quantum. So to Bob's question on disruptive, disruptive is definitely in the eye of the beholder. From a hardware point of view, I actually don't see quantum computing as being disruptive to me as an IBM systems provider. I see it as an enabler. Quantum computing is going to augment classical computers. It's going to enable us to do things that we were never able to do before. I mean, there's a whole class of problems out there that Danny was kind of touching on a little bit that are really just very hard to do with classical computing. We tend to sweep them under the rug. You guys tend to spend a lot of time trying to figure out best heuristics to go after them. But they are real problems that if we could find a solution to, would have disruptive impact on society. The first person who comes up with the best algorithm to get, a better financial portfolio optimization, the best person to come up like FedEx with the logistics, the best route from an optimization point of view, the person who can better simulate quantum chemistry, can come up with new materials, better drug discovery, et cetera, et cetera. So from that point of view, quantum computing is disruptive. But from my point of view as a systems provider or a hardware designer, NVMe, solid storage class memory, that driving software-defined storage, to me that is much more disrupting to my business and I think hardware design. And maybe we'll talk about that a little bit more in the panel. But quantum computing. All right, so what is IBM and other people in the industry doing? Danny talked a little bit about D-Wave. D-Wave is one kind of quantum computer. What I'm talking about is a slightly different kind of quantum computer, which is a universal quantum computer. I will try not to have any marketing in here. If I have marketing in here, feel free to raise your hand and throw things at me. So this is early days. If you're familiar on the right versus the left, they look very familiar, right? I mean, I keep telling people that we're really in the 40s in quantum computing, especially from the universal side. But we're at the point now where we're building real systems. IBM has had a system up and running, publicly available on the cloud, nonstop since May of 2016. So we've had a public cloud service that anybody can log into, run on a real quantum system, albeit small one, since last May. But we know how to operate these things. We know how to keep them calibrated on a daily basis. We know how to run them. We know how to keep the coherence times fairly stable over long periods of time, which is the first step you need to do to move into the next step, which is commercialization of the technology. So talk a little bit about universal quantum computers. So this is a nice bridge into the chart that was shown before on terms of what HPC does, what HPA does, and what kind of problems they solve. A quantum computer, a universal quantum computer, is really good at solving, or holds the possibility to be really good at solving these types of problems. Small number of bits in, large probability space where you're looking at 2 to the n probabilities, small number of problems out. Now, the good news is there are a lot of problems like this in the world that are non-polynomial, that are exponential. I won't go into NP complete, NP hard, blah, 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 blah. But what quantum computers hold a promise to do is there are a lot of problems that are NP hard, which may be easy for a quantum system. And those are the problems that it holds a possibility to be good at. We know that in the way foreseeable future, you have something like Shor's algorithm, which is for decryption, that has been proven to be quantum easy. But there are a lot of other problems that we believe will fall into that category as well. So we're very close to this point where we get to the size systems where you have 50 to 100 qubits. This sounds really small, but remember that possible probability space you can grow is 2 to the n. So 2 to the 50 is a larger system state than on the world's largest supercomputer. You can't simulate today a 2 to the 50 quantum computer and all the system state that can solve on the world's largest system. Now, I think that number will continue to creep up. It's like it was at 43 and it's at 45. It'll probably creep up to the 50, 60 range, over the next couple of years because people keep working on this. But someplace in the 50 to 100 space, you're going to see a quantum system that can, for a particular type of problem, can be done on a quantum system that you can't practically do on a classical system. When you get to about 1,000 to 5,000 range, then from our point of view, you start talking about production. You start talking about not just being able to run one molecule and simulate one molecule that you can't practically do, but run it on a continuous basis, looking at a lot of different molecules, looking at a lot of different kind of stuff. And then when you get up to 1 million, then you're starting talking about the holy grail, fault tolerant. But this is not in the next decade. Our belief is these two steps are in the next decade. So this technology is real. Right now it's at a state where the real computers that are out there that you get access to are less than 50 qubit size, but IBM, Google, other players are building it, so we will be here within the next few years.
Oh, great, thank you. That was all fascinating stuff. I appreciate the panelists for sharing their insights, and we'll get to the questions in a minute. But because I have the microphone, I'm going to go off script a little bit and just ask a question of the panelist. It seems like we have two different kinds of disruptive technologies up here. And to me, one of the disruptive technologies that I don't think we've actually identified as such is the idea of the stack, the implementation stack. And there's some folks up here now that are looking to fit their disruptive technologies somewhere into that stack, in some narrow slice of the pie there. And to those folks, I ask the question, can you be truly disruptive if your technology is such that it has to fit into the confines of a stack? You can only go so high above out of your implementation, and you can only go below so far into your abstraction. And I'm just wondering if you can be truly disruptive, or better yet, does the concept of the stack play a critical role in either limiting or perhaps even enabling disruptive technologies? That's a question for perhaps some of you. For ones who are completely out of the stack, and we can talk to the quantum folks there, would be an example of this. Can you compete against the stack idea when you basically have to come up with a solution that is essentially soup to nuts? You're not looking at an hour slice of the pie. You're looking at having to create everything from scratch. What are some of the pros and cons of living in that either stack or stack bar world? And so if we could just kind of get some folks to kind of talk about that for a minute. Earl, I'm sorry, I just wanted to ask that question. All right, cool.
So this one work? Yes.
There we go.
Okay. So basically I live on both sides of that fence. Full stack system, classical, full stack quantum. I think there's definitely advantages to having the full stack, and negatives. I would say that, to your first question, you can absolutely be disruptive as one layer in a stack if you provide such sufficient value that you're going to get, drive your technology in. You can look at examples like NVIDIA as an example. NVIDIA has been very successful at being disruptive in these kind of AI workloads. I think though, that in order to do that and really drive through that, true innovation, you need to have partners, like Mellanox, like IBM, to allow you to get that innovation to market, because there are some players in this industry who quite honestly are being choke points to innovation because they have, they have other motivation than, letting other people drive their innovation in the stack. And this is especially true when you're talking about I/O bandwidth, accelerators, and those types of things. So I definitely think it's possible, but no one of us on this stage, in my personal belief, can act alone. And even if you're talking about quantum, these quantum algorithms that we're developing are going to be hybrid quantum and classical, because quantum systems are really good at small data in, large possibilities, small data out. That is typically not the full application code. So even when we're talking about these quantum chemistry kind of examples that you'll see from any of these quantum players, that's partly classical routines, partly quantum routines, and you mix them, which is why we're doing Python notebooks, blah, 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 blah. But I don't think anybody is full soup to nuts independent stack. You need to partner.
Great, thanks.
Yeah, I agree that you can definitely be innovative and disruptive within the stack. In fact, I think the stack can actually be used as a tool in that way. It can be used to drive adoption, but it can also be used as a way to build a better together story. So in a lot of cases, you're going to be able to go off and be very disruptive in a unique way, in a very purpose-built way, outside of a stack. But once you start enabling that use with other technologies and use the stack as a unifying factor, I think you can actually drive more innovation and more uses. And that would be a case where using the stack, you can actually do both.
Thanks. The stack is a beautiful thing, right? Because it allows you to focus. You don't have to worry about solving the problem from hardware all the way up to the application layer. You can focus in this particular area. Speaking from the point of view of a guy who's only been thinking about quantum for the last 5 years, the development of a stack in our world is probably the most important problem, I think, facing us right now, because we have ideas about how you translate from an application down to hardware, but the tools and the layers of abstraction and the interfaces are, they're not well defined. And that means that people who enter this space, they don't have that stack which acts as a map and allows you to focus your attention on a piece of the problem. So I actually think that, I love your comment about, it's like the 40s. My boss actually says 50s, but, the sentiment is very similar. So I think that, back in the 50s in classical computing, we didn't have this notion of, there are loaders and assemblers and operating systems and link editors and blah, 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 blah. That's what we need in our world. So I'm gung-ho stack. Okay. Now, maybe in 20 years, stack will feel confining, but, I think it's a powerful tool for allowing big sets of people to make progress in complicated domains.
Great.
So speaking from the standpoint of someone as delivering an interconnect, we strive to work within the stack. We strive to be invisible and to accelerate within the context of that. But in making that paradigm shift from a CPU-centric to a data-centric network, introducing intelligence, it also creates the opportunity to perhaps reorganize or reconstruct the stack. And those types of things will only be possible with the innovations that we're bringing today.
I mean, I think I would echo all the comments up here, and I think the insight was actually pretty good up here. That is, that the enablement of some of this technology is the disruption, and that's within that stack. And certainly, from our standpoint, giving people access to various layers or more components within a layer through that stack is one of the things that is disruptive about the technology we're bringing.
Well, also agree with much of what's already been said. I'll give a slightly different perspective, being what I think may be the only business and marketing person on the panel. You know, I like to look at these things also as disruptive, also from the standpoint of how these things are taken to market. And we've have, I think, lots of examples of really disruptive technologies that have been developed in this particular market segment by companies that no longer exist because they could never really find a market for it, or simply didn't know how to take it to market. And so, you know, the question of is it a part of the stack, I'd translate that slightly different to is it a part of a real customer problem, customer solution that you can translate into. And that isn't necessarily a very big market. You know, a company can create a business with a disruptive technology that might be an absolute niche, but might be a terrific niche to be in because it really uniquely solves a customer's problem, really creates an answer to a problem that's out there that didn't exist before, and thus, you know, becomes monetized and is something that'll survive over the years. In other places where technologies have been absolutely, became pervasive later, but that the company created them couldn't figure out how to take it to market. My favorite example of all time being, of course, Xerox PARC, who created the mouse, created the graphical user interface, created everything that we use, you know, on a daily basis on our tablets, PCs, whatever, but never figured out how to take it to market. And others figured out how to do that and truly made it disruptive by doing that.
Great. Well, actually, I was hoping for a bit more controversy, so I'm kind of disappointed. Okay, that said, one of the things that I think the stack hierarchy helps establish is the rules of the road for partnerships. It probably makes it easier, and I think that's a really interesting unintended consequence of the stack concept. Can you guys address some of the issues in terms of the partnerships that you would like to get involved in or you think would be really useful in taking the disruptive technologies you've discussed here today and basically say if we had these kinds of partnerships, we could move even faster, get to market better, be cheaper, more effective, those kinds of issues?
Okay, I'll start this time. So yeah, you know, we look at it from Dell EMC, you know, from really sort of two types of partnerships that we look at very closely. One is obviously the technology partnerships that we have with folks like Intel, NVIDIA, Mellanox, and so on and so forth down the line, because we are absolute believers that to create the kinds of complete solutions that our customers really want, there is no one entity that creates, you know, the leadership technology in all areas. Mm-hmm. And, you know, to think that that's going to happen would actually stifle technology development. The flip side of that is the relationship with our customers, because I think a very important aspect of how we develop disruptive technologies is how we work with a network of strategic customers who basically, in a sense, creates our sandbox, who allows us to work with them to try out new technologies, try to see how they get applied in practice in their locations, as well as in our own labs, so that at the time that we actually look at commercializing them, we already have an understanding of what works, what doesn't work, and so on. Mm-hmm. And it allows us to learn from them. And there's a few of those folks are in the room here, TAC being one example of one of our partners, San Diego Supercomputer Center, Ron's sitting over there, are both partners of ours in doing these kinds of things. I'll mention this in my 15 minutes of fame tomorrow.
Yeah, I agree. I think our business partners are critical to driving some of those relationships that are actually happening with some of the hardware or technical partners that we also have here. And so in terms of, you know, they're coming with a specific problem or a specific workload that they want to accelerate, and we're in the business of trying to match that to some hardware underneath the covers that would actually solve that problem. And obviously trying to create some simple interface where if something better were to come down the train, we would be able to swap that out underneath. And that's Ryft's entire goal. So that's critical to our business, in my opinion.
Mm-hmm.
I'd probably just mention some of the technologies that we already support, things like GPU Direct, Arcuda. Those are examples of technology partnerships that have helped to build better solutions for a number of different applications. The key to having a standard interconnect is being processor agnostic, being able to support best performance on x86 or Power, ARM, or FPGA or GPGPU. And anytime a new technology comes along, that's where Mellanox needs to work together in order to try and bring the best performance out of those technologies.
I disagree with everything these guys said.
Thank you.
So I feel like that you're standing on the 50th floor of this beautiful office building, and us quantum computing guys are standing on the ground floor looking up. You take for granted the existence of this tremendous industry that knows how to cooperate, right, and build products that work with each other, which is a completely remarkable thing. We're trying to get to the point where we can have a relationship with ISVs that can produce software that will actually run on our platform. I mean, think how much more comfortable one of our customers would be if they could feel like they could buy a platform from us and then software from somebody else that would actually run on our platform. That's a baby step, So we're trying to make the escalator to get us up to the second floor. So partners are very important. So we're looking at it from the other side of the coin,
Right.
At Cray, we're always looking for partnerships with our customers. We want their problems. Bring us your problems. We'll try to solve them together. The partnerships with technology partners are always important from a system perspective. But I think if we look at this through the lens of the convergence that I was talking about earlier, we need an advanced partnership with university and between two very different user bases. You've got both of which have deep partnerships of their own, but not so much in between them. Cases where we see, if you try to scale Python, for example, and work with people who have Python code and try to get them to scale it in ways that we understand more on the simulation side. And vice versa, they look at it and they think that they have to understand Fortran in order to make advancements, and they think that that's a set it back. So trying to figure out a way to bring two different user groups through tool usage and creating other standards and things of that nature are places where I think partnerships could be developed that could really help.
Yeah, I'm with Danny. So for us, the rate limiting step, in my opinion, is going to be algorithm development. So it is creating two things. One, making it very easy for, and I say developers, I don't mean, these are like a special breed of developers where there probably is a couple thousand of them on the planet who, have, some understanding of quantum information science, have some understanding of linear algebra, et cetera, et cetera. So, algorithm development is our number one challenge. And, in terms of partnerships, it needs to be around those folks who are willing to work with us, who have industry domain understanding to create those algorithms on one hand, and the second hand is working with academic communities and government agencies around the globe to increase the number of people who have the skills to do quantum information science and quantum development. So I completely echo your thoughts. I mean, from a system stack point of view, we're in a little better shape in that we already have hardware vendors who can be partners, who are providing some of the components or can help us with some of the components. So hardware vendors are a little better shape, but algorithm development and basic education, high school all the way through graduate and postgraduate training is something we're putting a lot of focus on.
Okay, cool. Well, thank you very much. Just to give you a quick summary, Bob's rules of public speaking: number one, never do a live demo, and number two, never be the guy between the audience and lunch. So with that, I'd like to quickly thank our panelists for sharing their insights and philosophies today. I really enjoyed this session, so I want to thank all of you. And just basically invite everyone to head off for lunch. Come back in an hour. We've got lots of cool stuff in the afternoon. And I know Mary's probably got a really nice lunch set up for everybody. So thank you very much.